thank you for being here. I'll present a library and its Python bindings. So the library is called PETSc. PETSc stands for the Portable Extensible Toolkit for Scientific Computing. And so I've been told that many of you here are mostly doing Python, but you should be aware that PETSc is in fact a C library with also Fortran bindings and so C and C++ bindings. And so I'm not an expert in Python, so I'll try to make some live demos. Hopefully I won't make too many mistakes, but you'll be here to help me out, I guess. All the content, it's quite fresh. I made the tutorial especially for this occasion, and so if you want to follow along, you can get both the PDF of the presentation at this URL, and there will be also live demos that I'll try to redo on my laptop, but if you want to skip to the solution directly, you can also fetch some of the Python source codes directly there. Okay. So, first, again, I would like to thank you for welcoming here because, again, this is a fresh set of slides. So this is the first time I'll make this tutorial, and so I'll be happy to have some feedback if you have any. And don't take this as just a one-time thing. If you have any follow-up question after the tutorial, please feel free to engage, and of course, we'll be happy, either me or the other PETSc developers or PETSc for Pi developers, to continue working on your problems or your applications. So the prerequisite for the tutorial, let's say, basically are a C and a C++ compiler. The C++ compiler is in fact not mandatory, but hopefully if you have a C compiler, you also have a C++ compiler. So again, this is just to get PETSc compiled because PETSc is a C library. And so if you are doing Python, again, I guess you have a Python installation. The objective of the tutorial is basically to teach you or to let you know what is PETSc, what can be done with PETSc, and also again its Python bindings. And so there will be a particular focus on the second part of the tutorial on solving or preconditioning linear systems. But you'll see PETSc can be used for doing many more things and not just solving linear systems or preconditioning linear systems. Sorry, so this is basically the outline of the tutorial. I'll give a very broad introduction or broad overview of the infrastructure of the complete library. And then we'll follow mostly a bottom-up approach, basically, where I will first show you what are some of the lowest level objects within PETSc so that you can get a feel of what is going on under the hood. And then we'll go slightly higher by going into the matrices, and then going into Krylov solver, and then going into preconditioner. Okay? And so when it comes to preconditioning, I will give some particular focus on 4 types of preconditioning. So inexact or exact factorization, which are kind of the ideal preconditioners, multigrid methods, domain decomposition methods, and block decomposition for multiphysics problems. So when it comes to the infrastructure, so as I mentioned, PETSc stands for the Portable Extensible Toolkit for Scientific Computing. It's a very large code, so it's about 1 million line of C code. And so if you look at a top-down approach this time, at the highest level there are tools and there are functions and solvers to do time stepping or to do optimization. So for example, either implicit, explicit methods when it comes to time stepping. For optimization solver, we have PD constraint solver, interior point method, and so on. Below this layer sits the nonlinear solver, so scalable nonlinear equation solver, SNES. We have many tools like Newton method with either line search, trust region, quasi-Newton, so on and so forth. When you are using your favorite nonlinear solver, it usually boils down to then solving linear solver. So for the linear solver, we have what is called the KSP objects, so Krylov subspace package. For Krylov method, again, we have many available Krylov solvers like conjugate gradient, GMRS, pipeline Krylov method, block and batch Krylov method, so on and so forth. And so when it comes to Krylov solver, you usually also need to use some sort of preconditioning. And so again, these two types of objects, KSP and PC, will be the main focus of the tutorial. And so for the preconditioner, again, we have a wide variety of methods. So incomplete or complete factorization, QR factorization, overlapping domain decomposition method, substructuring domain decomposition method, block preconditioning, multigrid, either geometric or algebraic, and so on and so forth. So I won't focus too much on the domain management part of things, but this is basically all the infrastructure, all the plumbing necessary for basically dealing with either meshes. We can also handle adaptive mesh refinements, so for octrees, unstructured meshes, particle methods, staggered grid, and so on and so forth. So in this tutorial, I will only stick to regular grid. So you'll see some instances of what is called DA. But you can do also, of course, more complex problem, let's say unstructured meshes, but just for the sake of clarity and not going too much into the DM part of things, in this tutorial I will stick to regular grids. Okay, and so then if we go further down below the Krylov solvers and the preconditioners, we have basically all the linear algebra, the low-level linear algebra, so either vectors, index sets, so basically collection of integers, and then the matrices, which are in a very broad sense linear operators. And so we have different kind of format, as I'll show later on. You can have assembled matrices, so AIJ matrices like compressed sparse row or coordinate formats. You can have also have blocked formats, so you may know about the block compressed sparse row. For example, if you deal with vectorial finite element space or high order discretization node-wise. We can also have dense matrices, hierarchical matrices. So, for example, for compressing boundary element operators. We have also shell operators, so matrix-free, if you just want to supply to PETSc your matrix vector products. And we also can offload those matrices on the GPU, or they can also be directly assembled by the user on GPUs, either using CUDA for NVIDIA GPU, HIP for AMD GPUs, or also Cocos if you want performance portability. So when it comes to the communication and computation kernel, it's very standard, let's say. When it comes to multi-node computing, we rely on MPI. For the dense linear algebra at the node level, hardware-wise, we rely on BLAST, LAPACK, and so as I mentioned, Cocos, CUDA, HIP, and for dense linear algebra, the user is free to use ScalaPack or also Elemental. So just a quick overview of the development cycle and how we can engage after the tutorial. So PETSc is hosted on GitLab. So it's open source. You can make merge requests, you can post issues, you can make comments, you can review our merge request if you want. I'll quickly mention also SLEPC, which is a sister library of PETSc. I think it was, yep, just here. So SLEPC, so I forgot to mention, PETSc was mostly developed in the US at Argonne National Lab. We are about 16 developers. And so out of those 16 developers, I want to say that a good half of them are based in the US, but we are also a handful of European developers and also from Saudi Arabia. SLEPC, which is for solving eigenvalue problem, singular value problem, distributed large eigenvalue problem, is developed mostly in Spain. And so it's a sister library, so the design principle really follows what is done in PETSc. And so it's also hosted on GitLab. And just for the tutorial, at the end of the tutorial, we may have to use some of the files that we provide, not part of the official release of PETSc. So when you download the tar.gz or when you git clone the PETSc repository, we have another repository which is called data files, which is just a collection of like meshes and matrices which we use to benchmark or just for continuous integration. And so if time permits, at the end we may do some run and some preconditioner setup on some matrices that are available in this repository. But you can get all those freely, it's fully open. When it comes to manual and website, so there is 3 different important URL, let's say. So the first one is basically the user guide. So it's explained all the philosophy behind PETSc. It also it gives pointer to the C API. Then you have the manual pages, so basically all the API that is callable by either C or C++ code, and also Fortran code, but in some of these C API, there is sometimes a note saying this API, which is just for C, is not available in Fortran. And so the PETSc4Py, so the Python bindings, the Python API, tries to stick to the C or to the Fortran API, but it's on a different website. It's on the same main website, but it's a different URL. So when it comes to the API, the C and the Fortran API are matching in terms of casing and capital letters and whatnot. You'll see that for the PETSc4Py API, there are some twists, some here and there, but it's usually quite easy to figure out what is the counterpart of the Python API when you look at the C function. So I'll give you some more details afterwards. So if you want to get in touch with us, so there is a Discord channel. It's open. There are multiple threads depending on what you want to talk about. And if you are old school or if you are more shy, you can just reach out to us via email. So the PETSc users mailing list is open. It's archived. And so there are different questions from users, and you may get an answer from another user. PETSc dev, it's also archived, it's also public, but it's mostly if you have questions, for example, with respect to the API, if you want to add a new functionality or whatnot. And so the PETSc maint website, the PETSc maint mailing list is private. And so if you want to share, for example, problems that you are not at liberty to disclose with the outside world, you can reach out to us there, and it won't leak. Okay. So with any library from scientific computing, most often the difficult part is to get the library to be installed or to run. And so when it comes to PETSc, we have multiple ways to actually get it installed. So again, if you like the new shiny stuff available nowadays, you can do it via, for example, SPAC. So it's as easy as doing, for example, SPAC install PETSc, and you can also add a couple of packages. So for example, Hyper, which is a collection of multigrid solvers from Lawrence Livermore National Lab, and MUMPS, which is a direct solver from France. And so this will get you the C and the Fortran library, basically. But if you want to get it then to run in Python, you also, for example, have to install. So MPI4Py is not mandatory, but PETSc4Py will be mandatory. So just a small remark, MPI4Py and PETSc4Py are both maintained by Lisandro Dalcin, and so again the philosophy behind the two libraries are very similar. You can also do SPAC install SLEPC if you want to solve eigenvalue problem, generalized eigenvalue problem, singular value decomposition, or generalized singular value decomposition. And SLEPC also comes with interface to other packages like RPAC, Prime, and so on. When it comes to PETSc, we have interface with many outside libraries. So I think last I checked it was around 160 external packages. So not all of them are available through SPAC install, but you can do very SPAC install PETSc plus many packages like Metis, ParMetis, Scotch, SuperLU, SuitSparse, so on and so forth. So this is SPAC. I don't know if there are any SPAC users in the room. Okay, fine. Any pipe user? Okay. So pipe is like the more Python style, I guess. So you can again use a similar way for installing PETSc with pipe install. And again, MPI4Py is not mandatory, but it's just if you want to use MPI directly inside your Python code. And then you can do PETSc and PETSc4Py. And an important option to keep in mind is that, again, by default, if you just do SPAC install PETSc or pipe install PETSc, it will really install the bare minimum. So it's already very nice, but you won't have access to many of the external packages. And again, one of the strengths of PETSc is to be able to design composable solver where you can switch between different techniques. So like very efficient multigrid techniques, for example, and very efficient direct solver when the problem can be solved easily with a direct method and so on. And so with the bare bone installation, again, you can do already very nice, interesting stuff. But one of the strengths of PETSc is to be able to call natively many external packages for preconditioning or for solving or for meshing and so on, for partitioning and so on. Okay, and so as I said at the beginning of the, just before the beginning of the talk, I'm more old school, let's say, and so I prefer to do things from sources, but again, it's quite easy to do it from sources if you are familiar with the terminal and with Git. So again, you can clone the main repository. So by default, this will clone the main branch. So there are two principal branches in the PETSc repository. There is the main branch and the release branch. So the release branch is mostly for release fixes, and the main branch is for ongoing developments. But again, whatever gets inside the main branch must be reviewed, and so you can assume that the main branch is in working order. And so if you must decide between either the main branch or the release branch, just stick to the main branch because it's functioning and you'll have access to the latest functionalities. So when it comes to the release cycle, I forgot to mention, but every 6 years we release a main version. So we are currently at PETSc 3.23, and so at the end of for every 6 months we increase the minor version. So in September 2025 we'll go to PETSc 3.24, and in March 26 we'll go to PETSc 3.25. And so at the end of each month we increase the patch version. So we are currently at the end. The last tarball was generated at the end of April, and so it was 3.23.1, and so at the end of May it will be 3.23.2, and so on and so forth. And we ensure that there is no backward. We ensure backward compatibility. We try to ensure backward compatibility. So hopefully, if you have a script from PETSc, which is from like a couple of years ago, you should still be able to run it with a newer installation. This is mostly true for the C API and the Python API. There has been recent changes with the Fortran bindings, so this is not very true for the Fortran bindings. But I'm guessing there are not that many people doing Fortran in the room. A couple still, okay, that's fine. I work with people who do Fortran with PETSc, so that's no big deal. Okay, so building from sources. Again, it's quite straightforward. If you are somehow used to dealing with a terminal, you can clone the source or you can get the tarball. You either go inside the PETSc directory or you untar your tarball. And so one of the strengths of one thing I like about PETSc is that its build system is designed such that with a single source tree, you can have multiple installation. And so, for example, so I'm defining a variable which is called PETSc, which is common in most installation. And then you can define another environment variable, which is, for example, called here arctutorial. And so when you configure using this script, for example, here it assumes that you don't want to use the MPI from your machine. You want to let PETSc compile its own MPI. You want PETSc to install MPI for Pi. You want to activate the PETSc for Pi bindings, and let's say you want to download 2 extra packages, so slabc and HPDDM. Everything will be built and put inside a folder which is called arctutorial. And so then you have something which is, everything is contained in one directory. And so then, for example, you are at liberty to change whatever configure options you want, and then to use another PETSc arc, for example, arctutorial bis, with some extra packages, okay? And then you can redo make all, make check, and so basically you'll have 2 PETSc installation, and you are at liberty to switch between one installation or the other. So I will show you afterward in a concrete example how it can be useful. So why I prefer to do it from sources? Well, first, so I'm not very good at Python, so pipe stuff, I try to avoid dealing with pipe. I'm also not a user of SPAC, so we share something. And so when it comes to flexibility, it's very nice because if you have the sources, you can just edit whatever you want inside PETSc, and then you can recompile and you're good to go. Whereas if you are using some generated archive or some generated package, well, you cannot edit the PETSc source. So I'm guessing it's not very useful for most users, but as a developer, it's a must. And so as I mentioned previously, the fact that we can have multiple PETSc arc is very useful, especially since, as I mentioned earlier, PETSc is developed in C, and so the type of the scalar that are being used by PETSc is determined at configure time, in the sense that you cannot use a PETSc installation that solves problem, for example, in complex arithmetic and in real arithmetics at the same time. So at configure time, there is a parameter which is called with_scalar type, which by default is of type real. And so if you want to solve a problem in real arithmetic, fine, but then if you want to solve another problem in complex arithmetic, then you need to have another PETSc installation with scalar type equal complex. The same applies with the precision of the scalar. So by default, PETSc use 64-bit precision, but if for some reason you want to solve problem in quadruple precision or in single precision or even in half precision, you need to add another parameter which is with precision single float 128, and you need to reconfigure and rebuild PETSc. But again, you can have the same source, the same directory PETSc, and then multiple PETSc arc. So just for example, in my case, I have like, I have like a compilation in complex with optimized mode, real with optimized mode, real with 64-bit integer, real with debugging, complex with debugging, so on and so forth. Okay. So now we jump into the low-level objects. So the first object I showed the last object I talked about in the complete picture of the PETSc infrastructure was the index set. And so again, such index set, so basically collection of integers of PETSc int, it's called PETSc int in PETSc, are mostly used for doing data distribution. They can be used for gathering or scattering values either from a vector or from a mesh. And they are also often used for doing local to global or global to local mapping in a distributed memory context. So there are three types of index sets. The first one is what is called IS general. So it's for arbitrary index set. Then we have ES strided, which are used for regularly spaced integers set. And then we have ES block, which are used for block size, fixed block size lists. So the notion of block size in PETSc is quite important, and so I will show you what it means in practice. And what's also important to keep in mind is that thanks to the light layer of Python in PETSc we have it's easy to make index set interoperate with Python list. Okay? So in the C and in the Fortran API, we have access to raw objects, and so it's not that easy to make them interoperate with like the C library, the standard C and so on. With Python, it's quite easy to have everything interoperate thanks to PETSc. Okay, so this is I think this is the first set of the first example. Sorry. So I will try to start from scratch, and so okay, it's as I hope you can see in the background, in the back. So text. Okay, so the first thing again when you are dealing with Python and with PETSc will be to import PETSc, and so we can do something like this, and so I will also import the standard sys package, and so you can PETSc is closely related to MPI. So are you all familiar with the MPI standard? Okay, and so by default, when you import PETSc, it will automatically initialize MPI and also PETSc. Okay, so if you have done a little bit of plain MPI, you usually know that all main start with something like MPI initialize or MPI init, and they all end with something like MPI finalize. And again, if you deal with MPI 4Pi, you know that you can get away with murder and don't do any of this because it's automatically handled by the MPI 4Pi module. And when it comes to PETSc 4Pi, it's also automatically handled. One of the issues with this is that it's not parsing the command line argument, and so I think we can do something like this from PETSc 4Pi import PETSc. Okay, so when I'm looking at my screen, I'm just looking at my solution. So just give me a couple of seconds. Again, I'm not the most familiar with Python. Import PETSc 4Pi. Yep. Okay, I got it right. Okay, and so if we do this, okay, so we can do Python tree. What is the x1.py? Okay, this works. But for example, let's say I want to print out the help of PETSc. If I do this, nothing gets printed. And so again, it's by default because when you do the import PETSc 4Pi, it will initialize PETSc and MPI and everything without parsing the command line argument. And so if you want to parse the command line argument, you need to do the initialization yourself. And so this can be done with something like PETSc 4Pi.init sys.argv. Okay. And so now I have the help. Okay, so I must warn you, one of the strengths of PETSc, as I mentioned already many times, is that we have access to many different parameters, many different packages. It's also a weakness. It's very easy to get lost into parameters and to get lost in options and so on. And so this is a prime example. When you do help, you have like 100 lines of help, and we are still not doing anything meaningful. And so when we get to the solver side of things, you'll see that you can get really overwhelmed with thousands of options. And so I will try to give you the proper pointer and the proper options to look for and to look out for to have some meaningful help, let's say. So one thing which is important, for example, which can be done right away, is, for example, to use the version just to see what is the PETSc you are using. And so here you can see that I'm using a development version. So hopefully I didn't screw up my installation, but it should be okay. And you can see here, for example, that I'm using my architecture in debug real mode. So as I mentioned, it's useful to have multiple arcs. And so here, let's say that I want to do things more efficiently. And so I want to switch to the optimized version of PETSc, which is likely the one you'll have if you have installed PETSc through, for example, pipe, or through some external libraries, for example, Dolphin or FireDrake or whatnot. But one nice thing about Python is that you can play around with the Python path. And so, for example, I will switch from my debug arc to my optimized arc by just changing the Python path variable. And so now we can see, okay, I'm now using the optimized version, and so I can do some production runs, let's say. Okay, so I've loaded PETSc for Pi, I've passed the command line argument, and so I will write, for example, a simple Python list in this list range, for example, 7. Okay, and so I will print my indices, and so now, just to make sure everything's okay, I want to convert this Python list to basically an index set, a PETSc index set, and so I can do this quite easily by doing something like es general equal, so PETSc.is dot create general, I think, and then I can feed my indices. Okay, so nothing will get, indices, okay, sorry, es parentheses. Okay, so nothing gets printed. All the PETSc objects have access to what is called PETSc viewer. And so PETSc viewer are basically ways to save information or to load information from the user, either on the terminal or on the disk. And so there is a very useful option which is called view from options. Okay, and so you can do view from options, and then you can supply a prefix for registering basically an option name. So for example, here I will just call this es general. And so then you are at liberty in your command line to use the option es general and to have PETSc write or print information. So for example, you can do es general. So I will just remove this. Okay, I think I need to unset PETSc arc because it's being very verbose. Okay. Sorry, I forgot the dash. Okay, and so you have your information about your index set. Okay, so it's quite trivial here, but you can do more fancy stuff. So for example, if you want to export some information to some other software, you can do something like ASCII myes.txt. And so then you can open up your file myis.txt. So this is IS general, nothing very out of the ordinary, let's say. Then again, as I mentioned, we can do IS strided. So I think the API should be something like this: create strided or stride, create stride. And so then it's something like length. So for example, I will write an ES strided of size 5. I will assume that it starts at, for example, 4. And the step, so in between each index, it will be something like 3. Up. Okay. So all objects in PETSc, so IS, KSP, preconditioners, and so on, have access to PETSc viewers. They also all have PETSc options prefix, and so you can set a prefix to your objects. For example, by doing something like es strided set options. Set option prefix, and so for example, I will prefix this object by something like strided. And so when you set an option prefix, basically all the options must be prefixed by the said prefix. So for example, now if I do es underscore general dot view from option, so I will say is, for example, then the option on my terminal should be the name of the prefix, so strided, then the name of the option, so is. And so I think I put this, which is not needed. No? Strided is. Ah, of course. Yes, strided. Okay. And so now I need, it was okay in the beginning, I think. Okay, and so we have an object is whose prefix is strided, and so you can see what the stride means. We start at 4, and then we do increments of 3, so 4, 7, 10, and so on and so forth. Okay, so again, all those low-level objects are used for the preconditioner, for the Krylov solvers, whenever there is some gathering or scattering of value or exchange between neighbors in terms of MPI processes and so on. And so the last one, which is in the presentation, is es block. And so again, I will do something like es create block. And so then I can use a list, for example, I will say 0, 3, 7. And then I think so it's block size or BS. I always get it wrong. Just give me 1 sec. It's first the block size. Sorry. So let's say a block size of 3. Okay, and again we can set a prefix. So for example, set options prefix block, and then I can do es block set from options. Okay. And so again, block size in PETSc, it means that you basically, instead of, it means that basically all the index will be multiplied by 3, by the block size, and so we'll store, the indices will be contiguous, and so in practice, this index set will represent something like 0, 1, 2, 9, 10, 11, and then 21, 22, 23. Okay, so now, okay, let's forget about all this, block. Okay, and so again here we just show the block indices, and so I think we can actually convert this to Python style indices, and so we can do stuff like print es underscore block. So I think it's get indices and then to list. So get indices will basically convert the block indices which are shown there into standard indices, and then toList will convert the list of integers into a Python list, and so now we should get something like 0, 1, 2, 9, 10, 11, 21, 22, 23. Okay. I forgot to say, but if you have any question throughout the tutorial, please feel free to interrupt. If you want to go deeper into one aspect I'm showing or that I'm not talking about, don't hesitate. Okay, so I think that's okay. That's all there is here. Yep. So is set options prefix, view from options, and so this type of mixing options and prefix will be used quite intensively throughout PETSc and PETSc4Pi. Okay, so this is exactly what I just said. So again, it's not specific to is, it's common to all objects. So if you have a VEC, if you have a MAT, if you have a KSP, if you have a PETSc, you can always do something dot set options prefix and something dot view from options. Of course, for some objects, it won't make much sense. for example, it's easy to view a mat. A mat is just a collection of indices. I mean, an assembled mat like AIJMat. If you do mat.view from option, it will make a lot of sense. We'll see all the entries in the terminal or in the file. But if you have something like a matrix-free operator where there is no representation of your matrix, then if you do mat.view option, you won't see much things on your terminal. It depends on what you are trying to view, of course. But it will run. There will be no error at runtime. You may get more or less meaningful information, but that's just the way it is. Okay, so now we jump into vector. So the class in PETSc is quite easy to remember. It's called vec. And so in PETSc 4.py, it will be also called vec. And so in fact, now I will jump into distributed memory parallelism. So in the previous example, everything is run in sequential. Of course, it also runs in parallel. But here there is no parallelism involved in the sense that I will just run this, for example. So PETSc arc Darwin up the real pin MPI run. If I run this with two processes, I will basically get the same information displayed twice. Hopefully, the name is x1.py. Yeah, so there is nothing involving distributed memory parallelism. All the operations are done on each process independently, and so it's not very interesting. Now we'll actually jump into distributed memory parallelism. And so what's important to keep in mind is that in PETSc, again, all the objects, so vectors and matrices, and are distributed across MPI process using a contiguous row-wise decomposition. So if you think about a vector, basically, you have to think about different chunks of contiguous rows being held by each process one after the other. So you can access the global size of your vector using getSize, and if you want to know the size of the local portion of your vector, you can have access to this size using getLocalSize. Again, the block size must be compatible with the local and the global size. So for example, if you have a vector of size 4 and the first process holding 3 entries and the second process using only 1 entry, you cannot have a block size of 2 because it's incompatible with 3 and 1. So you can have access to the ownership range, so basically the beginning and the end of the contiguous chunk of rows using getOwnershipRange. And if you want to have access to the row memory behind the vector, you can do getArray. So again, the memory layout behind a vector is very straightforward. It's just a standard C array, contiguous array of size getLocalSize. Okay. So if you want to have a look at the solution, it's example 2, and so I will try to basically do it again live. So tac, I'm just copy pasting this x2.py tac. Okay. So first I will generate I will use some random sizes for each of the local portion of the vector. So for example, let's say I will run this. I think in the example, in the solution, I'm running this only on 2 processes, so I will 3 processes, sorry. So I will just copy paste this for good measure, for safety reason. Tac. Okay, so this code will only run with 3 processes, but it's just for the sake of the tutorial anyway. So some sizes, I don't know, let's say 4, 6, and 2. Okay, and so now let's say that each process, the process rank I will have a local vector of sizes I. So my local size is sizes petsc.comWorld.getRank. Okay, and so now I'm creating my vec, and so I can do the same as for ISs. So basically petsc.vec .create, and so I can say vec.set local set sizes. And so when you set the sizes, you can set either the local size and the global size, or just the global size, or just the local size. And so here I will just set the local size, so local size, and so I will let PETSc decide what is the global size. So basically what PETSc does is just a reduction of all the local size to determine the size of the global size of the vector. And so to let PETSc decide, there is a variable which is called PETSc.decide. I think it's all in capital letter. Okay, so first, let's run this with one process to make sure that we have a nice error. Oops, sorry, x2. This exam, okay, perfect. And so now, tack, okay, it runs. Again, we don't see much. So what can we do? For example, so I'm not sure if we can already view the vector because it has not been set up. I mean, we are creating it, but there is nothing to view yet, but we can try. We try to make error handling and error information as useful as possible. And so hopefully, if there is an error, this is something that we can make sense of. Sorry. No support. Okay. So this is not a nice error. This should be fixed because it's not. I mean, I can make sense of it, but I mean, I'm not sure you can. But basically, there are some missing information. So I will write a note for later. More meaningful error message. Okay. So something to work on the train back home. Anyway, so we'll set up the vector properly, and so to set the vector properly, we need to do something like, I think, vec set from options. And so then I think we can do this. Okay, I forgot to mention it in the presentation, but just before this, I told you about set options prefix, view from options, and so here I showed you also a very important parameter, which is set from options. So again, it's the same for all type of PETSc objects. So like math, vector, KSP, preconditioners, and so on. And so basically, this call will look at all the arguments that are inside the option database, and will try to make sense of the argument that you are supplying. And so it will set the vector. So basically here it will set the type of the vector according to whatever options you've supplied on the command line. And so for example, I could try to do something which will fail, but which is something like vec type CUDA, I think. So basically I want to tell the vector to be of type CUDA instead of living on my host memory. I want to leave it on a GPU memory. I don't have a CUDA capable laptop, so this should give me a nice error. Okay, a non-vector type, CUDA, because I don't have CUDA on my machine. So, but you can do stuff, and so by default here, the vec type, since we are doing distributed memory parallelism, is MPI. And it's also here. So for example, if I do something like sequential, I think this should also give me an error. Cannot create a vec sec on more than one process. Okay, so. And yeah, so again, the set from options, you'll see it later on, it's quite useful to parse, to automatically set up an object depending on the option database. And so the same as for the prefix, if I do something like vec.set options prefix, my vec, tac, then everything gets prefixed by myvec, and so it will be something like, oh, okay, this is stupid, but it will be my underscore vec type, I think. And it will be my vec underscore view. Sorry, up. Okay, so back to the error. The option is properly parsed, but it's a stupid parameter. So let's switch to something more meaningful. Okay, good. So now, of course, we need to put meaningful information into the vector. So again, two ways to do it. Here it's a vector, so it's quite easy. We can either do it like Python or C style. So basically, get the array and set the value like it's a standard array or pointer in C. So for example, we can do array equal vec.getArray. And then we can do something like for okay, so let's do for I in range, the local size is local size, perfect. Let's do something like array I equal something very stupid, but something like 10 times PETSc.com underscore world.getRank plus I. Okay. And so then we can view this vector. And so we have properly set the values. And so another option is to do it PETSc style. And so the PETSc style way of doing it will look closely, very similar with matrices, so it's important to see it right away. It's through the assembly routine in PETSc. And so the assembly routine in PETSc, I don't know if the assembly routine in PETSc are basically called set values or set value. And then you can tell to PETSc, I'm done with the assembly, so you can start assembly process. You can overlap computation and communication by doing some other unrelated computations. And so when you want to have access to the actual vector, then you need to tell PETSc, okay, I need to finish up you need to finish up the assembly and give me the hand back when you are done with the assembly and when I can use the actual vec object. So I will do it now. For example, again, we will do a simple for loop. So first, let me reset the vector. So the API for each of the objects, it's very large. So actually, in fact, let me go here. Let me go there. For example, we can look up vec set values. Okay. So this is the C API, but at the bottom of each page of all the manual entries, you can have access to all, for example, all vec routines. You can also have an index. You can have access to all math routines, all KSP routine, and so on. So if you go to the vec set routine, I think you'll see a vec set. Okay. And so if you go to vec set, you basically set all the components of vectors to a single scalar value. And so as I mentioned, there is not a one-to-one correspondence between the C API and the Python API, but in this case, it's just set with a lowercase s. So you can do just vec set, for example, 1.0. Okay, so now all the vector will be filled with 1. And so I will do a loop for A1. I can do, for example, vec.setValue. So interesting problem here. I can do vec set value I. For example, we can use the same. Tac. And so then you can tell to PETSc whether you want to override whatever is inside the memory or if you want to add whatever is inside the memory. And so you have access to either, so just up, you have access to either, where is it? I didn't use it in my correction, so let me just look quickly. Where can I look this up? PETSc for bindings, PETSc for add values. Okay, so it's PETSc insert mode. Tac. add values. And so I think by default, likely to be insert values. I will check this just after. Okay. So there is one issue with this problem, with this line of code. For example, let's say you are process 0. If you are process 0, you will set value for the row 0. Okay, perfect. And then row 1, 2, and so on. Now let's say you are process 1. You have I that goes from 0 up to local size -1. And so you are also inserting the value of the row 0. So you are basically overwriting with multiple processes the value, the position 0 or 1 or 2 and so on. And so there is two ways to circumvent this issue. You can either do something like R begin, R end equal, c'est quoi déjà? C'est vec.getOwnershipRange. And so then you can shift your index by basically the beginning of your vector, the beginning of the range of your vector. So R begin plus I. Okay. And so now all processes are in charge of just setting the value that are local to their processes. So in fact, we can do something like assert local size equal R end minus R begin. Okay. So I'm doing the assembly. Once I'm done with the assembly, I can tell to PETSc, okay, I'm done, do the assembly. And so we can do either assembly begin, assembly begin, do some stuff here. So for example, something which is nice to do is to sleep. So you can do PETSc sys sleep something like 0.1 times MPI rank, just for having a low load imbalance. And then once you are done, assembly end. Hopefully you can do something more meaningful here. Okay, and so let's again look at the vector. Okay, so we go again. Let's view from option, view with assembly. Okay, my vec view with assembly. Sleep, c'est quoi le problème? Ah, pas de S majuscule. Ok. Good. So it's the same as previously, but with all indices shifted by 1. So 0, 1 to 4, 11 to 16, and 21 to 22. Okay, and so okay, so that's one thing. Another thing, again, in PETSc4Py. PETSc4Py is very nice to learn about PETSc because there is a lot of simplification. And so, for example, if there is no meaningful work to do here in between the assembly begin and the assembly end, so the staggered approach, again, it's very nice if you have some computation where you can overlap computations, or so basically computation with assembly of your vector. So for example, you have in your computation, you can assemble a vec, do some other extra work, and just then use your vector. Of course, it's not very often that you can do this. In most scenarios, once you have assembled your vector, you need to assemble your vector and then use it right away. For example, if you are doing a linear solve, you assemble your right-hand side and then you solve using the right-hand side. You don't wait and you don't do some extra stuff. So again, in PETSc4Pi, you can simplify things, and so there is a utility routine which does basically both the assembly begin and the assembly end in one go, and which is just vec.assemble. Okay, and so as you've seen, PETSc has a lot of way to deal with options, and so you can also register your own options yourself. And so, for example, here I will show you how we can register a Boolean, for example, if you do some conditionals inside your script. And so here my conditional will be basically if I want to do some overlap, else. So this is the first part, the if, and this will be the else. And so it's something like if, so PETSc, PETSc.options, and so then it's get bool. And then it's something like sleep, why not? And so the default value, and so here I will use a default value of false. And so I will increase the sleep timer just so that we make sure that we are indeed sleeping. So this is fast and this should be slow. Yes. Okay. And so in PETSc, whenever there are Boolean options, so we can accept multiple types of value. So we can do, for example, false. We can do 0. I think we can do also false, and so on and so forth. No. I'm not sure if no is working. Oh, it's working. Okay. And so I think that's about it for vectors. Okay, so the main point again is that everything is spread out contiguously in terms of the layout. So here I have a vector of size what's the size of size 12 divided in size 4, 6, and 2. And so in memory, the indices are first stored on process 0, then on process 1, then on process 2. And so it will be the same for the matrices. There is always this contiguous representation. Any question or no?
I have a question.
Yep.
I'm confused about this vector.setValue function that requires the offset for the different processors. Because the example you showed before with the array, this wasn't necessary, so I'm kind of confused why each processor has an entire vector in memory.
So when you mean previous example, it was with the get array?
Yeah.
Okay. Excellent. So the get array, by definition of distributed memory parallelism, so we are not using anything like Fortran coarray or PGAS or basically global address space. Okay, it's purely MPI, so it's local address spacing, local addressing of memory. And so when you get an array, you get a pointer, a row pointer. And so by definition of distributed memory parallelism and MPI, we can only address the local memory of each process. So by definition, when we access the index 0 of the array, we already have the offset taken into account because we are doing local memory addressing. So in fact, this is one thing I wanted to show and that I forgot about, so thank you. There should be another routine in the at least it's in the C API, but maybe it's not in the PETSc4Pi API, but I think it's in the PETSc4Pi API. So you're correct that it can be a little bit misleading to have this offset. And so there is in fact another way to do it, okay? And so I will do it like that, and so it's to use the API set value local, which assumes that you are giving local indices. And so then there is no offsetting. And so you can do vecset. Okay, so let's switch it up a little. Let's do 2. And so now instead of set value, I will do set value local. And so then it's like when you have access to the row pointer, it's purely local addressing, so local indices. And so then I need to remove this begin. So in fact, I will remove it, and then I will rerun it just to see what's happened. And so I will just assemble this. No, in fact, let me try to use add. So instead of add values, I'm using insert values now. And so insert value will override whatever is in place. And so this one is useless. I will just put, I will remove this, but here I will use +2. Vec view with assembly list. Local vec local value. Okay. So I don't care about all this, I don't care about all this, and so it's vec view local. That's wrong. Just give me 1 sec. Vec set value local. The local row location of intéressant. Vec set. What? View local. That's puzzling. Just give me 1 sec. Set value local. So what is in the set value local? I'm not sure what is wrong with what I wrote, but printf style debugging. So these are the local indices. Location to write to, value to insert at index. Local. Let me see if there is a PETSc 4Pi example that uses this. Git grep set value local. There is no example, so maybe there is a bug. I'll need to double check, but I think you get the idea that you can use local addressing, local numbering for the insertion of the values. So again, a lot of work to do on the train. So I will give you an update about this. So hopefully, Donat, you can forward the information. But it should work. Maybe it's something I'm doing wrong in the PETSc 4Pi API. I'm sorry, I'm not very familiar with this. But yeah, you can supply this in local numbering as well, without the shift for the beginning of the portion of the vec.
So set value has potentially some communication between processors.
It can. So there is an option to. So you can, in fact. So that's one of the strengths of PETSc. So if we forget about this part, here you are able yourself as a user to set the value into another portion of the vector. So you are not forced to only setting the value local to your vector. You can have multiple processes write to some other location on some other process. And so this part in this part of the function call, there is no communication whatsoever. So it's basically stashing all the information. And so once you do the vec assembly begin, vec assembly end, then PETSc deciphers whatever you've done and decides, okay, you set the value which is not local to this process, so I need to send it somewhere else, and so on and so forth.
Okay, thank you.
And so in fact, this is why I was telling you about communication to computation overlap, because yeah, in this part, the vec assembly begin, vec assembly end. If you are setting value of some other process for the vec, then there is some communication like peer-to-peer transfer, like MPI send, MPI receive. I send, I receive. And so, yeah, this is communication. And so if you can overlap this with some computation, then that's nice. But yeah, there are possibly some communication. And so in fact, this should be avoided by vec set value local. I don't know why it's not working, but in fact, we can try something. If we put something like an arbitrarily large value, then we should get a nice value, like you are trying to set something which is not local to this process, even though you are using the matSetValueLocal API. So hopefully this crashes. This crashes, but with a terrible error. But at least, yeah, out of range value, it should be less than 12. Well, again, the error message is not right. It should be less than the local size of the vector. I need to figure this out, but I think you get the idea.
Yeah,
okay. Sorry about that. Okay, vector is done. Now we jump to math. I think vector is done. Yeah, math. Okay. So again, the same format, but instead of having just one component, one row distribution, we also have a column distribution. Again, it's important to keep in mind that even though we have a column distribution, all the process holds a contiguous set of rows. So the column distribution will just be used for the matrix vector product of the operation in general. And so I will show you again an example. So we can do the same ownership range, but now we'll be also able to do get ownership column range and so on. So yeah, as I mentioned, the column layout is just for the matrix vector product, because when we are doing a matrix vector product with x and y, your two vectors, x and y, may have different layouts. Okay? And so depending on the layout of depending on the layout of x, this will dictate the layout of the column of A, and the layout of y will dictate the layout of the rows of A. Okay, we need to be compatible such that we can do the proper MPI transfers and so on and so forth, the proper computations. Just as for vector, the block size must be compatible with sizes. So in fact, this is an interesting point. Okay, so again, this is nasty. I don't want this. I will fix it later on. But here, okay, so here it's an interesting problem. For example, we can do vec.setBlockSize. I think it's all capital letter. I mean, like that. So for example, we can do this. This should work. No. Okay, so here there is not much information about the block size, but for example, if we do something like 4 is compatible with the local size 4, but it's not compatible with 6, and it's also not compatible with 2, so we should get something like an error. Yeah, local size 2 is not compatible with the block size, and local size 6 is not compatible with the block size 4. So we'll just, okay, I've made my Python freeze, I guess. Tac, Python. Hop. Good. So let's go back to a block size of 2. Okay, and so same deal as before. Let's go to a new example. x3.py. So again, if you want to go straight to the solution, it's x3. Okay, good. Tac. And so I will call these row sizes, and then I will do column sizes. And so just as for vectors, you can create a matrix, and so you can do A equal PETSc.mat. Okay, let's try to use different sizes. So here the global size is of dimension. The global size is 12. Let's go again with something of size 12, but let's mix it up a little bit. So for example, we will do something like 1, 5, 7. No, sorry, 6. Okay. PETSc mat dot create, and so tac, and so again we can do mat dot set sizes, and so again we have the matrix layout for the rows first. So oops, sorry, I will do local, so r local equal row sizes PETSc dot comworld dot get rank, and then r local, so column local column sizes, tac tac. Okay, and so now I do r local again. Local, I don't care. Let PETSc decide the global size. It should be 12, and then again column local, and again I don't care. Let PETSc decide the global column size. Okay, and so again we can do a simple loop. So I think it's done in the example. I will just copy paste this because there is no real point with bothering you with this. And it's again the same as for vectors. Here I'm only so what I do is that I set the value for the local rows. So again, assert r local equal r end minus r begin. Assert column local equal column end minus column begin. Column r end r begin column begin. So I'm looping through the local rows, and I'm setting all the local columns. And so, yep, again, I can do the assembly once I'm done. And so the assembly, just as for the vector, if you don't want to overlap any communication with computation, you can just do mat. My mat here is called A. A dot assemble. And so now let's look at the matrix A dot view from options. Okay. So I think, again, this should run only with three processes. So Python 3, example 3. And so view from options, let's call this A view. A underscore view. Okay, global size 6. Just give me 1 sec. I think I got the order wrong. Local R size. No, the order is local. What is the issue?
I think the symbol should be with brackets.
Yeah, that's correct. But there is an issue even before. R set sizes. Okay. Sorry. The notation here is it's in between square brackets. Sorry about that. Okay. We get this. So let's put something instead of 0. Let's put 1 plus. Okay. And so here you are seeing your first PETSc matrix. So again, by default, we use something like the CSR format, so compressed parse row. There are many different formats. So for example, if you want, you can output this for MATLAB. So that way you can directly load this from MATLAB, and you can also draw the matrix. So it's not the most user-friendly drawing, but at least you have something to show. Sorry, X quartz. I think it should be better. Yep. Okay. So this is the matrix. So what does the matrix looks like? Again, if we look at the row distribution, we see that the first process has four local rows, then the second process has 6 local rows, and then the third process has 2 local rows. So far, so good. And then we look at the columns. We have 1 local column, 5 local columns, and 6 local columns. So the distribution matches. Again, it's very important to keep in mind that under the hood, PETSc, when it deals with the AIJ format compressed parse row, is in charge of all the columns for its local chunk of rows. The column distribution is just used for the matrix vector products. So now, for example, if we say that the process 0 must assemble a value, for example, for the second row, 5th column, it will be something which is local. It's stored by the first process, by the process number 0. It's not stored by the second process, even though it's not a local column. The notion of local and non-local columns is just for the matrix vector product. It's not for the underlying storage of the operator. The underlying storage is just done by row. It's just a splitting by rows. So if we go back to matrix vector product, what's going on with this Python? Activity monitor, Python. If we go back here, we can create vectors that follow the column and row layout of A by using the utility routine a.createVex. Okay, and so this will create 2 vectors. So I always get the order wrong. One which will follow the column distribution. So this will be the left. This will be the left vector, and then y, which will follow the row distribution. And so in fact, we can do something like assert x.get ownership range equal a.get ownership range. It's the column ownership range column. And then we can do the same for y. But this time it's just for the row. Pop up. Okay, let's give it a go. We can still draw the matrix. So we talked a little bit about this yesterday. By default, also PETSc has a binary format storage. So if you want to send us matrices, for example, you can use the binary and then the name of your file, so for example, a.bat. And so the assert are passing, so we have indeed compatible vectors, and so now we can do stuff like, for example, so the column, so x.set1, and then we can do y dot, so I think it's a mult x y, and so then we can do y dot view from options my mat mult. Tac. Whoop. Y my mat mult. Yeah, it's a vector full of 1, so there is nothing much to see. Okay. Okay. So what's important to see is that, in fact, the distribution of y and x are different. So here, if I do x view from option, so my mat mult. So in fact, here, let's play again with set options prefix. So x, and here we'll set options y. Okay, and so now if I do x my mat mult, and then y my mat mult, you can see again that the layout of x, so the input vector is like process 0 has a single row, then 4, then 5, I think, 6, 1, 5, 6, and the output vector, it's more like 4, 6, 2. Okay? So of course, this is something which is nice to keep in mind. If you are dealing with linear systems, most often the distribution of your of your matrix will be the same for the columns and the rows, because most people are solving square systems where the column and row distribution is the same. So you can assume that x and y have the same distribution, but it's something to keep in mind. For example, if you are dealing with rectangular problems, if you have like saddle point systems, it's most likely that your column and row layout distribution is not the same, and so you must keep in mind that the layout must be compatible for the operator and for the vectors. So far so good? Just let me check the solution, everything was there. And so I think next, okay, let me check. Yeah, so important to keep in mind again, in PETSc we have many different matrix types. So I just show you the Aij matrix, so for standard compressed sparse row, so you can think of low order discretization like finite element with Lagrange finite element, low order finite element, lower Lagrange finite element. There is the Baij matrix, so which is block compressed sparse row, which can be useful if you are dealing with vectorial finite elements, or like if you do high order DG and you want to have unknowns collocated on nodes. Then you have like the dense format, which is used for dense operator. And what we'll see also later on is the Python, so math Python and the shell matrices, which are matrix-free operators. So basically, the user is in charge of supplying its own matrix vector product. So if you don't do Python, if you just do C or Fortran, there are objects that are called shell, so math shell, PC shell, SNES shell, and so on. So shell in PETSc basically means matrix-free, so the user is in charge of supplying the information. And so if you go into Python, everything is called Python. So it's math Python, PC Python, I think there is a SNES Python, and so on. No, there is no SNES Python, sorry. But yeah, it's the same, Python and shell. And again, independent of the matrix storage, so whether you have a dense operator, or sparse operator, or whatnot, you must follow the same guidelines, basically set your values or provide your matrix vector product. And so once you are done with the setup, you can do assembly begin, assembly end, or just assemble. And this will tell then to PETSc that you are done filling in values or setting up the operator, and then you are ready to solve linear systems or to use the operator for doing whatever you want to do. Okay, so I think just before the break, we have a break. Okay. Just before the break, I will just quickly mention Dirichlet boundary condition. So it's not strictly related to PETSc, but if you've done a little bit of finite element or even finite difference or any sort of discretization with boundary condition, it's always painful to deal with Dirichlet boundary condition. It's something which is very trivial when you write it down, but implementing it and having it work nicely with the discretization, with the linear algebra backend can be quite technical. And so in PETSc, we provide utility routines to actually facilitate the implementation or imposing Dirichlet boundary condition. And so just for this slide, for clarity, I will assume that we have an index set JD, which is basically the numbering of your Dirichlet nodes. And so we can then complement this index set, so basically all the unknowns for which there is no Dirichlet boundary condition. And so we assume that we have a scalar value alpha, and that on the Dirichlet knowns, capital JD, we want to impose a value which is lowercase jd. So in PETSc, there is a utility routine which is called math 0 rows is. And so as its name suggests, it basically takes your operator A, and it will basically zero out the rows associated to Dirichlet boundary condition. It will put alpha times the identity matrix on the Dirichlet unknowns, and it will make sure that your right-hand side is consistent with the solution vector in which you have put the Dirichlet boundary value. Okay, so this is very nice. if I put this, if I put the C API, it may be because there is no Python API. Just give me one sec. Git grep mat 0 rows. Ah yes. No, it's in the C API as well, the Python API. But anyway, one of the issue, of course, with this technique is that if your A is symmetric, then this matrix is not symmetric anymore. And so, for example, if you think about Poisson equation with finite elements, well, in theory, you cannot use CG or Cholesky anymore, whereas you should be able to do it. So another way to do it is to use the other utility routine also available in PETSc, which is called this time mat0 rows columns is, which this time keep the system symmetric by lifting the right hand side. And so again, this can be useful to impose directly boundary condition, and this time the matrix remains symmetric if it was initially symmetric, of course. And so I think we can make a quick break. And so for the second part, we'll actually get into the preconditioning and the solving side of things. So we'll pick up where we left off. So I think now you've seen the very lowest object, so index set vector matrices. You should be able to get a sense of how are things distributed among multiple processes. And so now we'll jump into actually solving linear systems. And so we'll first talk about Krylov methods. And so more generally, iterative methods. In PETSc again, we are interested, you can be interested in solving linear systems, Ax equal b. So a small nice feature about the high level API, which is called KSP solve for solving linear systems, is that you can solve in place, so you can use the same input vector for the right hand side and for the solution. And so then, just as for the different matrix types, so MetaAJ, MatShell, MatPython, MatDance, and so on, there is a lot of KSP types. So the most famous one are, for example, the conjugate gradient, the GMRS and its derivatives like pipeline GMRS, block GMRS, and so on. If you are solving least square problems, there is LSQR, there is also CG on the normal equations, and I think that's about it. If you are interested in plain iterative fixed point method and not Krylov solver, you can use Richardson method. And if you don't want to do any sort of iteration and just want to apply your preconditioner, there is a KSP type which is called pre-only. So pre-only stands for preconditioner only. And there is also an alias to pre-only which is none. So KSP type dot none and KSP type dot pre-only will just apply your preconditioner once. For handling Krylov subspace method and KSP objects, it's the same as for matrices, vector, and index sets. So you can basically start by creating your KSP with KSP create. Then you can set its option prefix. Then you can set from options, so to parse all the options that have been set by the user on the command line. And so a key routine a key part of the API of PETSc and of PETSc 4Py is the dot set operators keyword. So what is the dot set operators? It's used to basically supply two operators that are most often the same, but just for the sake of thoroughness, I will explain the two operators that are supplied to set operators. So the first one in the PETSc lingo is what we call the A mat. So it's the actual matrix A, which is used in Ax equal b. So basically the operator that you use to do your matrix vector product, or that you use to do the factorization if you are using an exact solver for computing Ax equal b. Then you can supply another matrix, another operator, another mat, which is the P, which is in PETSc lingo what we call the P mat, and which this time will be an approximation of A. So for example, name it A tilde, which will be used to build the preconditioner on A tilde. So for example, let's say you have a matrix free operator A, okay, so you don't have the actual representation of A, you just have matrix vector product implementation, but you still want to implement some sort of preconditioner on A. For example, let's say the Jacobi method. Well, you need to be able to supply the diagonal of your matrix A, and so this could be used as your PMAT. So you mix a matrix-free operator AMAT with a matrix-ready PMAT on which you can build the preconditioner. You can also think about solving an indefinite system. So you have an indefinite matrix A, so you have a singular AMAT, but you somehow know how to regularize your system to build an efficient preconditioner on something which is not singular, and so you can think of supplying a slightly regularized PMAT. And so these are two simple use cases of two simple scenarios where you need to supply different AMAT and PMAT. But again, in most cases, you'll have a PMAT which is equal to your AMAT. So there are many available options when you use a KSP. So for example, you can do KSP monitor, which will basically print the iteration throughout the residual throughout the iteration. You can choose the norm that you want to monitor throughout the iteration. So for example, you all know about GMRS, most of you. So for example, if you use the GMRS, you may know that with GMRS you can precondition either on the left, or I think it's, maybe I will talk about this later on. You can change the norm type that you want to monitor, let's say. I will go back to this later on. You can decide to check the true residual at each of your iterations. So for example, again, if you go to GMRS, there is a cheap estimate of this residual which can be used to avoid doing some computation. If you want to check the true residual, you need to rebuild your solution vector at each iteration, so it can be a little bit costly, but you can force PETSc to do it. At the end of your linear solve, you can have PETSc compute the residual, you can have PETSc print why your KSP is converging, and you can also print your KSP with, again, KSP view, and I forgot, but you can also add the view from options as for the mat, the IS, and the VEC. So for this, I will start with a rather simple example. In fact, I'm only showing here simple example. It's the Poisson equation in either 2D and 3D. But again, I don't want to bother you with the discretization part of things. I want to focus on the mat and the KSP and the PC. And so I think it's the example number 5. And so just because rewriting everything from scratch will take me a lot of time, I propose that for this example I actually use the solution, but I will go through the example just to give you a feel of what is going on and what are we doing. Okay, so I will just get this file. I started working on this, but I didn't fix it yet. So curl minus O. Je sais pas si j'ai. Do I have Wi-Fi? Of course I have Wi-Fi. Example 5. Okay. So in this example, I'm basically solving Poisson equation in 2D, and so it will be a regular grid. So nx and y are the number of discretization points at each point. It's a simple 2D finite difference scheme, and so in PETSc, if you are dealing with structured grid, there is, again, as I mentioned in the beginning, a class of objects which are called DMDA, so data management of distributed arrays, and so you can use it for doing stencil computation on regular grid. Okay, so I won't go too much into the details, but basically it can be useful to create your 2D grid, and so again it's simple finite difference with centered second order scheme. So you take the derivative on the left, on the right, above, below, and so you end up with the standard 2D 5-point stencil, let's say, and again you can feed that to PETSc using a create Python matrix. And so this time it will be a Python matrix, and so you can see here that I'm defining a mult operator, And so the mult operator is basically the definition of your matrix vector product. So the input is the x, the output is the y, and so I just need to give the operation, the product y equal x. So this is done through a Python matrix, and so I need to give a context. So basically, if you know a little bit about object-oriented computing, it's just basically setting the implementation of a specialized class, which is the math class, and so we override the math mult operation with whatever is inside the Python script. Okay. So this is for the operator. We just know the action of the operator on a vector. And so then you can also, of course, discretize your right-hand side. And so here I'm just using a random right-hand side. And everything should be okay. And okay. So I will show you what we get. Tac. So I think this one can be run on arbitrary number of processes. Okay. And so it's example 5.py. Okay, so by default, I think nothing gets done. And so we go back to the slides. And so, for example, let's start with KSP converge reason. Okay, the script runs, but why is it stopping? And it's stopping. So something is terminating, but is it terminating for a good reason or for a bad reason? Let's check this out. Okay, so you can see here that the linear solve has converged due to converge Ertol, so the relative tolerance has been reached in 17.8 iteration. Okay, so you can in fact tune the relative tolerance, and so for example, if you increase the Ertol, KSP Ertol, I said increase, so by default it's 10 to the power of minus 5, so if I increase, let's do for example 10 to the power of minus 3, it should converge slightly faster. Sorry. 57 iteration. So far, so good. So maybe next you want to see the iterates throughout the linear, throughout the convergence of the Krylov solver, because, for example, you want to benchmark iterative method, and so you can do KSP monitor. Okay. And so here you can see the residual decrease throughout the iteration. The first the 0th iteration is basically the norm of the right-hand side. And so you can see that if you do 10 to the power of minus 4 times 10 to the power, divided by 10 to the power of minus 2, you get roughly 10 to the power of minus 3. So the relative tolerance has indeed been reached. So it's a little bit verbose, so I will remove that for now. Let's say I want to look at the KSP. So what is actually being done? So if you have looked at the code above, of course you know what is being done. But just for good measure, let's check. If we do this, we can see that we have a KSP object which is running on 4 processes. Perfect. We are using a Krylov method of type conjugate gradient. We have a maximum number of iterations set to a very high value, but we don't really care here. We have the relative tolerance, absolute tolerance. We are doing left preconditioning, and we have a preconditioner which is of type Jacobi with a type Jacobi. So basically, just the inverse of the diagonal as a preconditioner. And so, what is important also to notice is that we have an object of type Python. So again, it's a matrix-free implementation. So again, here it's a little bit weird because we have a matrix-free implementation of Python, but we are able to do Jacobi. That means that somehow PETSc is able to fetch the diagonal of the matrix. Okay, and so that's because in the script, if you go above in the class Poisson, in the class Poisson, I've implemented a method which is called getDiagonal, which tells to PETSc how it can actually fetch the diagonal. And so in this scenario where it's simple finite difference, the diagonal is quite trivial to get. It's just a center. I think center. Yeah, it's just the weight of your middle point in your 5-point stencil. But now, if I, for example, comment this out, tac, So now we are doing matrix free again because we just have the matrix vector product, and we have no way for PETSc, there is no way for PETSc to actually fetch the diagonal. And so if I'm still using a Jacobi preconditioning here, I should see that, there is an error because there is no way to get the diagonal of my operator. Okay? So in this scenario, we are kind of stuck. Basically, we just have the matrix vector product, so there is no way to do any sort of preconditioning. And so the only type of preconditioner which will work will be something like KSP type, PC type, none. Oop. Ah. Okay, so the problem, of course, is not too difficult. And so here it converges in the same number of iterations, whether we use preconditioner or no preconditioning, but it's a trivial Poisson regular grid, so that's no big deal. Okay, so let's go back to this, we fetch the diagonal, and so of course, again, if we try to use something more fancy for the preconditioner, like let's say we want to do an LU factorization, so exact factorization. Again, here, this will, okay, so I did the bookkeeping myself in the Python code, but if we are not so smart and we remove this, we'll get an error, because again, we are using a matrix of type Python, so basically a matrix-free operator. We want to do an LU factorization, but we don't have the matrix itself, so it's impossible to do LU factorization. Okay? And so when it comes to math Python, so the matrix type Python, you can implement some routines. So for example, you can implement, so there is the mult. You can also implement the multiplication by the transpose, because there are some Krylov methods, for example, that use both y equals ax and also y equal a transpose x. So for example, I think if we use the BiCG stab, so let's go back to Jacobi, for example. So this runs, and so now if I do something like KSP type BCG stab, I think it's this one. No, I think it's IBCG stab. Yeah, this one is the transpose. And so again, we don't have implemented the mult transpose operation, and so this does not work. Okay, so we go back to something which is functional. So for example, we can even use minres, I think. Okay, so minres, Jacobi, and so in this script, actually, I wrote down a code to actually draw the function, the solution vector. I think. Okay. So of course, we can increase the grid size, and so as we increase the grid size, it should take longer and longer to converge in terms of iterate, and also in terms of runtime. So far so good. Let me go back to the script. Okay, so one thing which is important to keep in mind, so let me put back the assert, is that the order of the operation matter a lot. So for example, here you can see that line 94, I'm setting up the type of the preconditioner, so I'm doing PC type Jacobi, and only then I'm calling KSP set from options. Okay? And so for example, if on the command line I use something stupid like PC type LU, again I will run into an error. I will run into a PETSc error. Could not locate factorization type LU with matrix type Python. Okay, so we've seen this. We've seen already before. But now, if I switch the order, then line 94, the KSP. I forgot to mention. But when you do KSP set from options, it's also called under the hood PC set from options. The PC associated, the preconditioner associated to the Krylov solver. And so if I flip the order. So line 94, the preconditioner associated to the KSP will be of type LU. So in theory, this should fail. But then in line 95, I'm resetting the PC type to Jacobi, something which is okay. And so this won't fail. Okay. So be very careful when you call set from options, depending on what you've also set in your code, it can overwrite some options that you've hardwired in your script. So in fact, the traditional way, let's say, of doing things in your script is to set some default option that you want the user to use by default if he's not supplying anything special. So let's go back to no drawing and like 32 by 32. Okay. So by default, let's say that the user won't do anything fancy. Okay. And so after you've hardwired the proper value for your solver, then you can do the KSP set from option. So if the user somehow wants to try something more fancy, so for example, instead of CG, use minres, he is at liberty to do it. But yeah, most often you'll want to set default values and then use set from options. But of course, you are also at risk that the user sets wrong value. So for example, again, if I use a PC type LU, then it will fail. But yeah, keep in mind that the set from options can overwrite some of the parameters that you've set in your scripts. And so you need to be careful with respect to the ordering of your calls. Okay. So what's also important to keep in mind is that PETSc can be used to do composable solvers. And so basically at runtime, depending on the set of options you'll use, you'll have more and more options that are becoming available. And so for example, by default, if I use minres and if I do help, okay, so let's go back in sequential. If I use minres and I print the help, then by default, for example, if I do grep gemres, I won't get any information with respect to gemres. I just know that I can use gemres. But now, instead of minres, if I switch to gemres, I will basically have a new set of options that are becoming available, which are only specific to gemres. So of course, if you use minres, there is no point to exposing to the user something like KSP gemres restart because it doesn't make any sense. So depending again on the set of parameters that you use, there are some new options that will become available. And so this is something that we cannot tell you beforehand, and it's automatically adjusting at runtime depending on your options. So for example, now that I have gemres, I can do something like KSP gemres restart 100. Okay. And of course, if I use minres, then this option does not do anything, and in fact, it's printed at the end. Be careful, you are setting options that we are not using, probably because there is a mismatch between what you think you are doing and what is indeed being done by PETSc under the hood. So in fact, here the mismatch is simple. We are not using gemres, we are using minres. Okay, any question with respect to basic trade-off methods or how we use KSP? No? So just I think it's down below with it's down below in the solution file, let's say example5.py. If we go back to the slide, here I proposed a very simple application where you need to use a different AMAT and a different PMAT. And so in fact this is done in the solution file. So if there is another parameter which is called PMAT, so if I turn this on, so PMAT is just an option which is specific to this file. But if I run PMAT, it basically use a KSP with a different PMAT than the AMAT. And so in this scenario, the PMAT is just the diagonal of the AMAT. Okay? And so here you can see that I have setting the operators A, so the AMAT, the matrix-free operator, which is just doing the mat mult. And then I have the PMAT. And so the PMAT in this instance is just a simple diagonal matrix with the diagonal of the AMAT as its diagonal. Okay, so first I fetch the diagonal, and then I create a new operator, which is just a diagonal operator. Okay, and so I reset my solution vector, and basically I solve the solution. I solve the same problem, and so I think it's in this scenario again. It's converging in exactly the same number of iterations because I'm solving the same problem because the Jacobi preconditioner on A or on the PMAT, since we are using a diagonal PMAT, it's just the same. So what's interesting here is that you can see at the end of the KSP view, in the case where we are using the same PMAT and AMAT, that we have the linear system matrix, which is equal to the preconditioner matrix, so the matrix Python, the matrix tree operator. And in the case where we are calling set operators with A and P, it's being printed out, and so we are seeing linear system matrix followed by preconditioner matrix. So basically, it's the way of PETSc to tell, be careful, you have a different AMAT and PMAT. And so the AMAT is indeed the Python matrix, and the PMAT is indeed the diagonal matrix. So all good. Of course, this runs in parallel as well. Tac, tac. Let's remove this. Okay. And so again, we have the same number of iterates. It's a simple problem. Okay. So again, so I've talked a little bit about preconditioner. It's because preconditioner has, KSP are always, most often tied, they are always tied to a preconditioner. And so whenever you create a KSP, there is also a PC which is attached to the KSP. Okay? And so when it comes to preconditioning, as I quickly mentioned before, you can either think of left preconditioning, or you can also think about, right preconditioning. So one thing to keep in mind is that not all Krylov solvers handle both left and right preconditioning. So for example, if you use the conjugate gradient, you can only precondition on the right with standard preconditioner. You can only precondition on the left with standard preconditioner. And for example, you cannot monitor the unpreconditioned residual. You are only able to monitor either the natural norm of the residual or the preconditioned norm of the residual. When it comes to GMRS, for example, you can precondition on both the right or on the left, but with left preconditioned GMRS, you can only monitor the preconditioned residual, the norm of the preconditioned residual, whether if you precondition on the right, you can only monitor the unpreconditioned norm of the residual. Okay, so it's a little bit technical if you are not familiar with left and right preconditioner. I'm sorry, but it's just important to mention. And so, for example, let's check it out on this example. So I will copy paste all this, tac. And so if we put this back on there, so we forget about this because it does not matter. The PMAT, okay. Sorry. Tac. So this. Tac, and so let's forget about this one. Tac. We go back to KSP view just for good measure. Okay, so we are using the GMRS, and so we are using right preconditioning with an unpreconditioned norm for the convergence test. And so, for example, if we move from unpreconditioned to preconditioned, we should get a nice error message. KSP GMRS does not support type precondition with preconditioner sign right. And so if we go back to left preconditioning, it will work all right. Okay, we have the number of iterates, so far so good. And so again, if we try to precondition on the left, but to monitor the unpreconditioned residual, we should get an error because precondition on the left implies that you are monitoring the preconditioned residual. Okay. So I will quickly mention some preconditioner. So you can think about exact factorization, LU, Cholesky, QR in PETSc. So these are most often coupled with pre-only. So you basically just want to do one forward and backward substitution and don't do any sort of GMRS coupled with those forward and backward substitution. So it's most often tied with KSP type pre-only. There are also inexact factorization. So ILU, ICC, incomplete LU, incomplete Cholesky. And so this preconditioner will return a matrix, so it will be a new mat, and you can actually choose how this mat is computed using the PC factor mat solver type parameter. So you can let, for example, PETSc compute an ILU factorization, or you can let MUMS compute a Cholesky factorization, you can let Pardiso compute LU factorization, you can let Suitsparse compute a QR factorization, and so on. So there are many external packages that can be used. Okay. There are also many other preconditioners, for example, Jacobi method, point block Jacobi if you want to, if you have like a non-trivial block size. If you want to make sure that your problem is consistent and well posed, it's always nice to start with a small problem and do a small SVD decomposition just to make sure that you have something which is well posed. So you can do PC type SVD. If you are solving small linear system, but on many processes, you may want to look at redundant or telescope preconditioning, which are basically doing data redistribution to avoid communication overhead. If you want to do inner-outer solvers, you can use a PC of type KSP. So you basically use a KSP as a preconditioner. So you do a KSP as an outer solver with a KSP as the preconditioner. So this is what we call inner-outer preconditioning. And again, you can do shell or Python preconditioning where you basically supply the action of the preconditioner on your vector. So you can supply the action of the operator A, but also of the preconditioner. So there are about 53 PC types, so there are many, many other preconditioners. And so in fact, throughout the rest of the presentation, I will focus on some other preconditioners. Okay, so again, as I mentioned earlier, PETSc is known to be able to compose options and to compose solvers. And so in fact, the very first kind of composable preconditioner is what is called the block-Jacobi method. And so the idea of the block-Jacobi method is basically to approximate again the inverse of the PMAT using only local inverses that are local to each processes. Okay? So it's a very nice preconditioner because it's embarrassingly parallel. You hopefully are able to break down the complexity of setting up the preconditioner on the full PMAT by just doing the setup on the local diagonal blocks of your PMAT. And so it automatically creates sub-Krylov subspace sub-KSP and preconditioner, which are automatically prefixed by the dash sub underscore prefix. And so I will show you an example, in fact, or do I show you an example? Yeah, I can show you an example. And so again, I will use, so I will now jump from matrix-free preconditioner, or matrix-free assembly, let's say, to matrix-ready, because for the rest of the talk, most of the preconditioner will assume that you are able to assemble a matrix, so a PMAT or an AMAT. And so TAC, I will use the example 6 TAC. TAC. So it's basically the same script, but it uses an assembled AMAT instead of a matrix-free AMAT. And so we'll be able to define new sets of preconditioner. So you can see I'm still using a DMDA. I'm still using the simple finite difference stencil. And so the assembly routine is somehow different because again now this is a matrix ready method. So I am assembling A explicitly, but the code is basically the same. And so here, for example, you can see that I'm using this type of preconditioner. And so I will run this script just to make sure that I did not break anything. So KSP. Okay, we are still solving the same Poisson problem. And so as I mentioned here, I will try the block-Jacobi method, and again we can prefix the option for the sub preconditioner using the sub prefix. So TAC, PC type block-Jacobi, sub PC type LU, for example, KSP converge reason. Okay. So this is what we get, and so what sub PC? Just one sec. Okay. So I need to comment this out, I think. What? KSP set. Sub.
I think you wrote subtype and not sub.
Ah, thank you. Sub PC type. Yep, thank you. Okay. So now I will show you. So block Jacobi, we have 4 processes. So by default, we are using 4 subdomains. So the 4 diagonal block. And so the sub-preconditioner, by default, we are using an exact factorization. And so we are coupling the exact factorization with just a pre-only. So we basically just apply the preconditioner. So now I will show you, something which is not necessarily recommended, but something to show how we can do diagnostics in PETSc when it comes to runtime and performance. And so basically you can see that in the script I have a Boolean condition. Let's say if I want to put load imbalance, I basically switch for a single subdomain the subsolver to something like incomplete Cholesky with a Richardson method and with 10 iterations on each subdomain. So basically I have 4 subdomains, 4 processes. 3 of them will compute an exact value factorization for their subdomain solver or subprocess solver, and 1 of them will use a Richardson iterative scheme with 10 iterations of incomplete Cholesky. Okay. It's not a very good choice. It's just to show you how we can do diagnostics with respect to the performance of PETSc. And so for this, I need to run with the option load imbalance. Okay, so you can see in the KSP view that by default, local solver for only the first block are being displayed. So if you want to display all the information for all the blocks, you need to use this additional parameter. So KSP view TAC. Okay, so I'm still solving the problem. But what we can see is that indeed, for the process number 3, we are using ICC with Richardson. But for all the other, we are using something like pre-only with LU. Okay. So again, something that you should not try at home, but I want to show you now what you can do and how you can profile your applications. So to profile your application, there is a parameter which is called logView, okay, which will basically time all the operation inside PETSc. Okay, so it will print a lot of information. Don't be scared. But it's a nice way to have a lot of information with respect to all the operations. So first you can see all the creations and destructions, so basically all the operators that PETSc or that you are creating or destroying. So for example, you can see that I am creating 9 matrices and destroying 9 matrices. I'm creating 16 vectors, destroying 16 vectors, and so on. So the number of creation and destruction should always match. If it don't match, it means that there are some memory leaks. And then the important part are all the timings. And so here basically you can see all the operations that are being carried out under the hood. And so for example, you can look at the matmult, so basically matrix vector product. And so you can see the number of events that are being triggered. So here you can see that in this execution I'm running, there has been 186 matmults. You can see the time needed to carry out those matmults, and so the important part is this column, which shows the ratio between the highest and the lowest processes. So basically you can see that there is a huge load imbalance because the ratio between the two is 11, whereas of course you want it to be as close as possible as 1. If you have a ratio of 1, it means that the slowest and the fastest process are taking the same time, so you have perfect balance. So here I will go back to load imbalance, and for example, I will put load imbalance to false. So here, all the subdomains are doing the same thing. So we should have a good load balance for the. So it's PC apply on block. Okay, so we have a perfect load balance 1.0. PC apply on block is basically the time spent on each of the local subdomain solver. And so now if we switch back to load imbalance, true, we can see, hopefully, that no, it's still the same. Maybe I need to make the problem slightly bigger. Why is it still no, sorry, the ratio is on the, let me just make sure. Yes, sorry. This was the ratio for the number of events that being triggered. I was interested in the ratio in the time spent. So it was not the second column, it was the fourth column. So here, indeed, we have a load imbalance of 9.7. So that means that the fastest process is 9.5 times faster than the lowest process. And so if we go back to load imbalance false, hopefully this is lower. So it was 9.7, 9.7 versus 9.7 versus 1. So here, all the subdomains are the same, and so we have perfect load balance, and so you can see the impact of the load imbalance. Okay. So of course, again, it's a very stupid example. It's just to highlight that the log view output can be really useful to do some very fine tuning, fine profiling to get both the timings and also the load imbalance in your computation. And so if you see a very high load imbalance, it probably means that there is something being weird going on with respect to the partitioning of the domain by the discretization kernel, or that you may need to adapt some of your solvers, let's say. Good. So inexact factorization, it ends at noon. Donat. When is the cutoff time? 12:30. Ah, good.
1 hour to go, and maybe 10 minutes for questions.
Okay, perfect. So inexact or exact factorization. I will start first by the inexact factorization. They are seldom used. Sometimes, for example, in smoothers for multigrid methods, but still, it's not the most efficient techniques. But anyway, there are two important parameters when you use, for example, PETSc to compute incomplete LU or incomplete Cholesky factorization. It's the type of shift that you want to use for the incomplete factorization. So again, if you are solving ill-conditioned problems, sometimes you need to add some shift to the factorization for stabilization purposes. And there is also the level of fill-in that you want to do in your incomplete factorization. So if we go back to the script, so I will remove the load imbalance. Okay, it's already off. So now all the subdomains are doing the exact same computation. So they are basically doing a subdomain. It's an exact LU. So let me switch to inexact LU, sub-PC type ELU. Okay, So we see that by default, PETSc does ILU with no level of fill-in. So by default, by the way, the default KSP and preconditioner option in PETSc. So if you don't tune anything, if you don't play around with KSP type, PC type, and whatnot, so the default PC and KSP type is GMRES with a restart parameter of 30, preconditioned by block Jacobi with ILU subdomain solver. Okay, so these are basically the default parameter. And so, for example, let's say that I want to add some fill-in. So here we have no fill-in. So we can see that the subdomain matrix is of size 496. And so it has 200 non-zeros, and so 20,000. Sorry. And so if we add some fill-in, so let me just put this. Okay. So if we do the same thing, but this time we add some fill-in, and so we do sub PC factor levels, let's say for example 2. Then we should be able to see that we have indeed 2 levels of fill, and so now of course the matrix becomes slightly denser because we allow some fill in the factorization. Okay, and so maybe just for the sake of completeness, let's say vi log to fill the t. If we do a full fill-in, so basically we switch back to LU. So it's a 2D problem, so it should not be too terrible. It's still. Tac. So we basically multiply by 6 the number of non-zeros from the factorization without any fill-in to the factorization with full fill-in. Anyway, this is the kind of statistics that you can get with the KSP view or the PC view, in fact. Yeah, so as I mentioned, KSP automatically creates a PC for you, and when you do KSP view, it automatically also does a PC view following the KSP view. Okay. Tac. Now I will talk a little bit more about mumps. So mumps is a the PC factor math solver type PETSc is available by default. You don't need to install any sort of packages. When it comes to PETSc, you need to add either the plus mumps or the download mumps when you configure PETSc. But it's a state-of-the-art direct solver. It can be used for doing sparse LU or sparse Cholesky factorization. And so there are a couple of nice parameters, let's say. So the first one is mostly for diagnostics. So it's not very useful for production runs, but if you want to figure out what is going on, why is it slow, why is it too fast, or whatnot, this is useful. And then the 2 other parameters are in fact very useful. The ICNTL 28, so the nomenclature for the parameter for mumps are not decided by PETSc. We stick to whatever is done inside mumps. And so if you have ever looked at the mumps documentation, you can see that they have like a list of 40 parameters which are all called ICNTL 1, 2, 3, 4, 5, 6, 7 up until 40, and they have also real control parameters, so just CNTL, and it's the same. You have CNTL 1, 2, 3, 4, 5, 6, 7. So the name is not very self-explanatory, but it's the way it is with mumps, and so we just stick to this nomenclature in PETSc. Okay, so ICNTL 28 is used for the symbolic factorization. I will tell you slightly more about this later on. And then the ICNTL 35 and the CNTL 7 are used for the numerical factorization and for doing what is called block low rank factorization. So first, ICNTL 28, again, I mentioned it's for the symbolic factorization. So when you do exact or inexact factorization, it's almost always split in 2 phases. The first phase, which is called the symbolic factorization, which is used in theory to decrease the fill-in in the factorization, and then a step which is called the numerical factorization, which basically computes the L and U factors. So in fact, if we go back to LU and if we do log view here, we should be able to see those 2 times. Tac, log view. Tac. If we go to the event timers, yep, we can see here LU factor symbolic and LU factor numeric. Okay, so these are the 2 steps, and so there is also those 2 steps if we switch to Cholesky. Tac. Where is it? Match Chol factor sim and match factor Chol numeric. Okay. So these are the 2 timers to keep in mind. Okay. So the problem is tiny. It's simple. It's in 2D. So I propose that we switch to a 3D problem. And so I think I have one ready for you here, example 7. It's exactly the same, but this time it will be in 3D. Okay. Tac, and so now we can do nx. So let's start slow. 32, 32, and y, and z, sorry, 32. Okay, so again, now we switch to exact factorization. So for example, LU. Oops, sorry, LU, this, KSP view, okay. And so let's say, for example, that you start with PETSc. Okay, for the moment, forget about whatever I said about MEMS. PC factor, math solver type, PETSc. So spoiler alert, this won't work. And we get a nice error message. Math solver type PETSc does not support matrix type MPI AIJ. So basically, the factorization that you can do with PETSc are only for sequential matrices. So just when you run in sequential or when you use PC redundant to centralize a problem on a single process. So that's one of the reasons why MEMS is nice, because MEMS handles distributed memory LU and Cholesky factorization. And so in fact, if you don't supply this, so the PC math factor solver type, by default it will use MEMS if you have it installed on your machine. Okay. So, what do we have? We have that we indeed converge in a single iteration, okay, because we are using an exact solver. So in fact, we can do a KSP monitor. Okay, so the residual goes to 0. We good. We're still using CG again. Probably here we can use pre only. It's no big deal. And so we are using an LU factorization, and so we are using MEMS to do the factorization. Package used to perform factorization, MEMS. So it's 3D now, and so you can see that the fill-in gets much, much larger. We go from 32,000 to a billion non-zero. Is that correct? Yep. No, 10 billion. Yeah, 10 billion non-zero. 10 million non-zero. And so, of course, if we increase the problem size, we should get something which starts to get a little bit slow. 64. And so, for the sake of comparison, let's look at the timers in the log view. Maybe I picked a too big problem. Ah, no, it's okay. Okay, so we go back to log view. Okay, and so again, what we see here is that, okay, in fact, it's taking 2 seconds for doing the symbolic factorization, 8 seconds for doing the numerical factorization. So the techniques I'm proposing here to show you the impact of this option are mostly suited when you are dealing with very large problem. Okay, so solving a linear system in 8 seconds, I think we can all agree that it's still manageable. So I will try to make the problem even slightly bigger, but I don't want to spend too much time waiting on MEMS to do its job. Okay, let's try this. Are there any other meaningful information in the log view? Let me just check that everything is indeed spent in the factorization. Yeah, okay. So we can see in the column of the timing here that all are sub-millisecond. Oh, yeah, the forward-backward solve is about a millisecond. And so everything is indeed spent in the matrix factorization. So it's very a difficulty for MEMS. Okay, this one is very big, I think. I mean, not very big, but too big. Okay, let's try to increase just one dimension, maybe. So of course I could increase the number of processes as well, but it's not, that won't help me make my point. And so while this runs, I will copy paste the options. So first I will look at the diagnostics. We could go back to the 64 by 64 by 64 problem, but I think 8 seconds it's too fast. if you want to know, if you want to see any impact of the parameters I'm proposing. Okay, so so yeah, okay, so 4 seconds and 30 seconds. Okay, so the first parameter is just for months to be a little bit more verbose, and so for example by default you can put a parameter of 2, and so again this time it's not PETSc which will be very verbose, it will be months which will be very verbose, and so you can see a lot of the details. So I don't want you to understand everything, I just want to show you the important point. For example, here we can see that for the symbolic factorization we are using METIS. I mean, MEMS is using METIS. We can see that about 3 seconds is spent in METIS for the symbolic factorization, and so this roughly matches the time that we have for the MAT-LU factor sim. Okay, so that's nice. And so then it should enter the numerical factorization. And so you have all sorts of statistics when it comes to the amount of memory needed for the factorization and whatnot. And so at the end we should get, okay, elapsed time in the numerical factorization is 31 seconds. And again, this should match nicely with the PC factor, the MAT factor numeric. Okay, 30 seconds. So everything is matching between PETSc diagnostics and MEMS internal diagnostics, so far so good. So first step is to switch from METIS to a distributed graph partitioner. So for example, we can try PARMETIS. And so this can be activated with this parameter. Again, the problem is tiny, so it was 4 seconds. I'm not expecting much gains here, but let's try it. I think by default we need to supply a value greater than 1 for distributed memory graph partitioning. Okay, it's using parameters. Okay, so already we have some nice gain. We go from 4 seconds to 1.2 seconds. Okay, so 3x speed up, not so bad. This should not impact too much the numerical factorization, but we'll just let it run for the sake of completeness. It was about 30 seconds, if you remember correctly, and so we have to wait 30 seconds, I guess. And okay, 29 seconds. So again, just gains when it comes to the symbolic factorization by switching the graph partitioner. Again, the timings inside the PETSc log view should match. MAT-LU factor, okay, 1.6 instead of 3.9 or whatever, and with METIS, and 2.9 instead of 3.0 for the numerical factorization. So far we've not changed the numerical factorization. So for the numerical factorization, we can use block low rank. So the idea of block low rank is to basically compute an approximate factorization by doing QR factorization of some of the matrix inside the factorization, and then to basically truncate the factorization. So it turns the exact factorization into an inexact factorization, and the way the parameter CNTL7 can be used to say to MEMS the level of approximation you are allowed to make. Okay, so first we try it with this parameter. So this parameter will turn on the approximate factorization, and so then we need to use the second parameter, and so the second parameter will be there to say up to which level you are ready to sacrifice the quality of your factorization. So let me try first with a very low threshold. So for example, I will use n to the 8 to the power of minus 10. So basically I tell to MEMS that I don't want to do any compression and to have almost an exact factorization. So here, then I should see almost no gain in the numerical factorization. So we are still using parameters for the symbolic factorization. So we have a little bit of gain there, and for the numerical factorization, we should see no gain. In fact, in this scenario, we may have a small overhead because, of course, it's doing slightly more operation to try to compress, but then we are telling that we don't want to do any sort of compression. So let me go back to okay. Sorry, there is already some gain. So we go from 30 to 26, so not gigantic gains, but still what's important to keep in mind is that, so we are activating block low rank, and so we have a dropping parameter for the accuracy of the factorization, which is set to 10 to the power of minus 10. And so we can see that already with this very high parameter, we are able to only store half of the entries that we would have if we were to do an exact LU factorization, and we are able to do 1/4 of the flop of the exact factorization. So it's already quite a drastic gain in terms of flop and in terms of memory. Again, it does not translate directly to timings because this problem is small, and so there is some extra bookkeeping that must be done to perform those compression. But I think if we decrease this further down, we can actually get some, hopefully, some timings improvement as well. Or in fact, maybe now we can switch back to the 128 by 128 problem. I will just see here. Okay. So the parametrize phase, it's always the same. Okay, I think it's a little bit faster. Okay, so now we are performing 1/10 of the flop. And so this translates to, okay, we have gained 7 seconds. So it's not that bad. And so the question is, how many iterations do we need to actually get to the solution? Okay, so what's important to keep in mind is that with this tolerance, of course, you decrease the quality of your factorization. And so you turn your exact solver into some sort of preconditioner. And so now you can see that, in fact, MEMS needs to iterate a little bit to actually get to the solution. And so we need 2 iterations to converge to the proper solution. So maybe we can try to decrease this, but we can try to increase this. Tack. Okay, so the block low rank factorization, so again, it's tightly connected to hierarchical matrices, and so it works very nice for operators that come from a PDE, like Poisson or Helmholtz or stuff like that. If you are dealing with very unstructured matrices that are not coming from PDEs, if you are dealing with different kind of operator, you can try it, but you should not expect such nice results. For Poisson problem, it's very working. It's doing wonders. Okay, so you can see that maybe this is a fun experiment. You can see here that the factorization took 40 seconds, and so I propose that I let this run without block low rank, and we can see how much time it takes. And so in the meantime, I will continue with the rest of the tutorial. So still parametrize, still some output. Okay, we let this on the back burner. Tack. Okay. So I think this is all for exact factorization. Of course, there are many other alternatives. I mentioned SuperLU, Scholmold, Paradiso, PETSc, Strumpack. So Strumpack and PETSc also have those sorts of block low rank hierarchical compression for exact solvers. So if you want to check them out, Strumpack in particular is able to, it can do factorization on GPUs, and so yeah, that's about it. You can also couple MPI together with OpenMP, and so you can rely on a multi-threaded BLAS to further benefit inside the direct solver. So this is also a nice feature of direct solver, or compressed factorization. Okay, so now we jump into multigrid methods. And so I don't know if you're all very familiar with multigrid methods, so I will just start with very theoretical motivation, let's say, of multigrid preconditioning. And so for this, I'll assume that we are again solving Poisson problem with a finite difference stencil on a 1D grid. And so if you look at, for example, the damped Jacobi preconditioner, you know that if you have like a Richardson scheme, you have an estimate, you can compute the error with respect to the exact solution at the iteration k plus 1, and so you can use the propagation matrix, identity matrix minus m minus 1 times a to the power of k. And so basically, depending on the eigen decomposition of this operator, you know which are the frequency of the error that you will dampen, that you will lower, and which part of the error you basically won't touch. And so again, if you look at a uniform 1D grid, you end up with such an operator. And so what is nice about this operator is that you can compute its eigenvalue and eigenvector explicitly with a closed formula, and they basically boils down to these eigenvalues. And so what's important with these eigenvalues is that if you look at j close to 0, so j close to 1, sorry, so basically the low frequency of the error, you have a sign of 0, so basically 0, and so you have basically a mu which is close to 1. And on the other hand, if you look at j close to n minus 1, you basically have a sign which is close to pi over 2, and so it's 1, and so mu is close to 0. And so basically, these kind of preconditioners, which are very simple, are efficient for lowering the high end of the spectrum, but very inefficient at lowering the low end of the spectrum. And so the motivation for doing multigrid is to basically have a grid of a hierarchy of grids on which the low frequency error of the high level grid will become the high frequency into lower grids, and so on and so forth. And so you can use this grid hierarchy to damp the frequency iteratively at each level. So if you just look at a simple 2D grid, you can write it like that. You first smooth your linear system with a very simple like Jacobi method with some initial guess. Then you compute your residual. You restrict your residual onto a coarser grid, and then you solve your coarse grid error using a coarse operator which is of lower dimension, and then you go back to the fine grid and so on and so forth. So of course it's a two-grid scheme. This can be extended to an arbitrary number of grids, and so the idea is simple. It's just to treat this coarse solver as yet another multigrid technique, as yet another two-grid preconditioner, and so you end up with different kind of cycle which are all usable in PETSc. So for example, this is the V cycle, and you can have full multigrid, you can have W cycle, and so on and so forth. So just as for the log view parameter, which can be used to display important metrics, when you do KSP view, you can also have access to important metrics when it comes to multigrid technique. And so the important metrics for multigrid are the grid complexity, which is given by this algebraic identity. So basically, it's the sum of the size of the operator divided by the size of the fine grid matrix. And you also have the operator complexity, so it's exactly the same, but instead of the size, it's the number of non-zeros in your matrices at each level, divided by the number of non-zeros on the fine grid matrix. So ideally, you want this as close as possible to 1, because basically it means that storing your grid hierarchy costs nothing. It's all dominated by your fine grid operator. But in practice, it's difficult to have this very close to 1. But for example, for symmetric definite positive system, we can have this close to 1.2, 1.3, and so it's still very, very efficient. So there is, again, a particular set of API, either in PETSc4Pi or in C, depending on whether you want to do geometric multigrid or algebraic multigrid. So I will start first with the geometric multigrid machinery. So if you want to do geometric multigrid, the main point is that you need to basically be able to build a grid hierarchy, or you need to be able to tell to PETSc how it builds a grid hierarchy. So for example, with the DMDA, the Cartesian mesh, you can tell to PETSc to build a grid hierarchy by refining the original DMDA. Okay? And so you can specify how many levels you want, what kind of cycle you want in between your levels, what kind of smoother you want to use at each level, what kind of solver you want to use for the coarse problem. You can also say how to go from one grid to the next or the other way around, depending on whether you supply the interpolation or the restriction. And you can also supply the set Galerkin. So I think this routine is actually not exposed in PETSc4Pi. Otherwise, it will be something like dot set Galerkin, but no big deal. This is rather technical, so not very important for now. And so again, it's yet another kind of composability in the sense that you'll have subdomains, you'll have smoother at each level, and so you can specify whatever you want as KSP and preconditioner for each of the level. You can have access to all of them. You can specify the options either on the command line or in your script and so on. So I won't focus too much on geometric multigrid. I will go directly into algebraic multigrid. And so the most important parameters, I think, for algebraic multigrid, especially if you are working with vector-valued finite elements, is to set, for example, the null space. So if you think about linear elasticity, I will give the null space afterwards. And also important is the block size, and if you don't know the near null space, you can specify the coordinates of your nodes, and PETSc can automatically build it for you. Of course, this only applies if your problem is something like elasticity. If you are dealing with some exotic operator for which the near null space is not the rigid body modes or the translation or rotation, we cannot build anything for you. But if you are dealing with something like elasticity, we can automatically build the near null space for you. So again, if you think about elasticity, so two-dimensional elasticity, if you use a standard discretization, the block size of your operator should be 2, and you should have 3 rigid body modes, so translation along x, translation along y, and rotation along the z-axis. If you do 3-dimensional elasticity, your block size, again, if you are using standard discretization, should be 3, and this time the near null space, so the kernel of your operator should be, the near kernel of your operator should be of dimension 6, 3 rotation along each axis, and 3 rotation along each axis. Again, for elasticity, so if your problem is exactly this, but you don't know how to discretize the translation and the rotation using your favorite package like Dolphin or FireDrake, PETSc can automatically assemble them if you supply the nodes of your the position of your nodes using the PC set coordinates API. So in PETSc there are 3 algebraic multigrid solvers. There is GAMG, which is basically the in-house algebraic multigrid solver. So you don't need to do any sort of download GMG, it's automatically there for you. So the most important parameters, at least from my hand, to play with when you are using GMG is basically the threshold. So the threshold is a little bit like the threshold in block low rank. It's used to basically tell how you want to build the grid hierarchy depending on the values in the operators. So you basically drop the values that are higher than the threshold, and so the lower the threshold, the more information in your operator. Then you can use the parameter aggressive coarsening, which is used again for defining how your grid hierarchy is built. So the default value is 1. Don't try to play with this if you don't need to, but if you want to fine-tune GMG, this is something important. The default smoother in GMG is Jacobi. So this is only true since PETSc 3.19, so I think about 2 years ago, mostly because before that it was SOR. but doing SOR on GPUs is quite difficult because it involves doing a backward substitution. And so since 3.19 we have switched by default to Jacobi because Jacobi on GPU is very easy to do. And so GMG can run fully on GPU if you are using GPU. So we had to change the default to make it more efficient on GPU. I'm not a big fan of this move, but this is the way it is. And so there are also fancy parameters to estimate the eigenspectrum, the eigenvalues of your operator, which by default is GMRS. You can, for example, switch it to CG if your operator is symmetric, positive, definite. But yeah, that's just again very advanced fine-tuning. So first, I want to see if MEMS finished. It did. Okay. Surprise, surprise. So just. So it was slightly above 1 minute, and before that, with block low rank, it was 40 seconds. Okay, so we gained 20 seconds, so it's not that bad just by adding a parameter. I think we can play around with this much more. This can be really useful. So just to give you some idea, block low rank was used by the MEMS people to solve a problem with 500 million degrees of freedom. Okay, so this is not the typical test case that you can handle with just an exact factorization. If they were, it would have been impossible to do such a large factorization with an exact factorization. And so block low rank plays an essential role in MEMS nowadays because they are able to use it to solve very large scale problem with an exact factorization, which is in fact not exact anymore, but anyway. Okay, so we switch back to true iterative solver with through preconditioning, and so we go back to PC type GMG. Okay, so let's remove log view. Let's do now a big problem because everything will converge in a blink of an eye. Maybe not so fast. Okay. Tac. So, for example, here you can see the grid and operator complexity that I mentioned earlier. So the grid complexity it's the lowest of the two. And so you can see that we can actually get quite close to 1. And so here the problem is quite easy. We converge in 7 iterates. But for example, if we want to switch back to SOR, we can do something like MG levels PC type SOR. But I think it will be difficult to beat 7 iteration. Maybe we go to 6. I think we went to 6. No, still 7. Anyway, the problem is too easy. So it's difficult to see any sort of difference. Maybe we can play around with the threshold, but again, for this problem, the defaults are quite good, so there is no real need to play too much with those parameters. Let's try to decrease the threshold. So of course, it changes the quality of the preconditioner. It changes the grid hierarchy. And so here we can see that it's taking slightly more iterates to converge, but it does not mean that it's slower because probably, yes, here in fact we can see that the operator complexity is slightly lower. Before it was 1.5 if I'm not mistaken. Where is it? Yeah, it was 1.5, and so now with the threshold parameter, it's slightly lower. So even if it converges in more iterates, the grid hierarchy has less non-zeros, and so you can expect the operation to be slightly faster. So it's always a matter of fine-tuning and finding the proper trade-off and whatnot. So we can try, in fact, with a higher threshold. And so I think this should make the operator quite dense. And no, sorry, the other way around. Okay, so here the threshold is so high that basically GMG is not able to build any grid hierarchy, so we have only a single level, and so it's basically doing just SOR on the complete problem, so it's not very efficient. Okay. Another preconditioner that can be used for algebraic multigrid is Boomer AMG, which is developed at Lawrence Livermore National Lab. So this one must be enabled. It's not done by default, and so it's enabled using the download hyper flag. And so, again, you have the same kind of parameter. So, for example, strong threshold is the equivalent of threshold for GMG. Coarsen type is a little bit more difficult. It's the way the build hierarchy is built, and relax type all is the same as MG levels PC type. What's important to notice about Boomer MG, about Hyper, is that you have the algebraic multigrid for standard nodal pointwise H1 discretization, let's say, but you have also access to AMS, so the auxiliary Maxwell solver for problem in H curl, and you have also ADS, which is the auxiliary divergence-free solver for H div problem. So if you try to solve, for example, Maxwell equation with GMG, it's likely that it won't work. GMG is mostly for H1 problem. Okay, and so last one, so we can try this on the Poisson problem. It will just work as well, PC type hyper. It may even be slightly faster. It was really optimized for Poisson equation, so it should be extremely fast. So 4 iterates. And again, so here, so by default, we don't have the grid hierarchy, but I think it's something like, this is the magic parameter. If we do that again, we'll have the operator and grid complexity displayed on the terminal. Okay. So you can see, in fact, here that the operator is much denser. It's denser. Anyway. So maybe if we play around with PC hyper Boomer AMG strong threshold. Shoot. Any better? A little bit better. About the same. Anyway. Okay, and so the last algebraic multigrid solver available in PETSc is ML, but it's an old version. So ML has been renamed now Mulu. So it's an algebraic multigrid solver which is developed by the same people as Trilinos. So it's mostly developed at Sandia National Lab. But Mulu is the new version, and in PETSc, download ML, still download the old package, so the old ML from like 14 years ago, 15 years ago. And so, I won't talk much about this because it's quite old and it's not very... Stick to GMG or Boomer MG. Okay, so now domain decomposition methods. So the historical method was introduced by Schwarz in 1870, so at one time where there were no parallel computing. So it's funny because Schwarz is in the genealogy tree in the coffee room. If you go back, you'll see Hermann Schwarz on the tree. Anyway, and so he used his algorithm when he initially designed to solve Poisson equation on what at that time was called complex geometries. And it was complex in the sense that back in the days, 2 centuries ago, people were able to solve Poisson equation only on square and, on rectangle and ellipses using Fourier transforms. And so the idea of Schwarz back then, of course, there was no computer, there were no finite element method, and so the idea was basically to solve the Poisson equation on the weird domain by decomposing the weird domain into 2 easier domains, so basically a rectangle and an ellipsis, and then basically apply Fourier transform on each of the domain and come up with an iterative scheme for solving such a problem. And so, of course, then a century later, with the advent of parallel computing, we also realized that this is naturally suited to distributed memory parallel computing, where you could think of, instead of doing an exact factorization of the problem discretized on the full problem, compute factorization of the problem stemming from each of the subdomain, a little bit like block Jacobi, but this time with some sort of overlap. And so in what comes next, we'll basically have to introduce 2 operators. So what is typically called in the literature Ri, so the restriction operator from the complete domain omega to just a subdomain omega I, and also the Ri tilde operators, which are just the same as Ri, but scaled on the overlap, so zeroed out on the overlap, such that you don't sum up multiple contributions from unknowns on the overlap. So if you take the transpose of those restriction operators, you basically end up with the interpolation operator, so Ri transpose. And again, there are a lot of connections with multigrid methods, and so in particular with the restriction and prolongation operators from multigrid. Okay, so you can see domain decomposition method as a type of multigrid method, or you can see multigrid methods as a type of domain decomposition method. The name of the game is how to find the proper R and P. So in PETSc, you can use domain decomposition methods, and in particular the additive Schwarz method preconditioner using PC ASM, additive Schwarz method, ASM. And so you can set the subdomain, so basically omega 1 and omega 2, in 2 different ways, either using the set local subdomains. And so you can use some information coming from your mesh, for example, and so you can add yourself some layer of overlap and you can feed that through an index set to PETSc. Or you can also let PETSc automatically define the overlap by just looking at the sparsity pattern of the matrix. Okay? And so for that, you, for example, go back to a matrix. We assume here it's decomposed into 4 subdomains, so it's algebraic subdomains. So we have the first chunk of rows which corresponds to the process 0, then the second chunk of rows to the process 1, so on and so forth. And so, for example, if we look at the subdomain number 2, 0, 1, 2, so the diagonal block is here highlighted in blue. And so PETSc can look at the sparsity pattern, and in particular the sparsity pattern of the off-diagonal rows and off-diagonal columns, and it basically can define an algebraic overlap by looking at the non-zeros outside of the diagonal blocks. And so here you basically have in blue the interior unknowns, and in green the overlapping unknowns, or the unknowns on the overlap. So with this, so of course, depending on the definition, whether it's algebraic or whether it's geometric, you can define the same set of operators, so the restriction and the prolongation operators. And so then you have access to different preconditioner types, ASM types. So the basic additive Schwarz method that was introduced by Schwarz 2 centuries ago, but which was algebraically formulated much later, can be written down like this. So it's basically a sum for all subdomains. So here capital N is the subdomain, the number of subdomains of basically the local operators. So RIA, RI transpose basically means that you take your full operator and you restrict it to just your local subdomain. And so you associate a KSP to this operator. And so, of course, it's of much smaller dimension. So, for example, if you want to do an exact factorization, it's much cheaper than factorizing A. And so there are a lot of variants. So, for example, there is the restricted additive Schwarz, where instead of the Ri on the left-hand side, you have the Ri tilde. And there is also non and interpolate, which are basically combination of Ri tilde either on the right-hand side or on both sides. But this is quite technical, and there is usually no need to play around with those methods. So this is very nice, but the problem is that you have actually no guarantee that this will converge when you increase your n. So basically, as n increase, the condition number of your precondition operator tends to blows up. And so this is quite straightforward to see. So for example, here it will be a 1D Poisson problem. And so I'm using a simple additive Schwarz method. And so you see that basically if you let the algorithm converge, it takes a lot of iterates to go to the actual solution. So just like with damped Jacobi method, we are able to very quickly kill the high frequency of the error, but getting the appropriate low frequency solution. So basically the global shape, propagating the information throughout the domain takes a lot of time. Okay. So this is one thing, and so the other thing is that for difficult physics, it's difficult to make them converge. Sorry, I went the other way. Up, let me go back the good way. So for example here, this is a difficult problem like a 3D linear elasticity instead of Poisson. And so if you do Cholesky with MEMS, it takes a lot of time, but it converges to the proper solution, so good. If you use restricted additive Schwarz, you can see that the setup time is very low, so wonderful. But it does not converge in the end. So there is no real point in having something which is really cheap to assemble if it does not converge in the end. So for domain decomposition method, you need to introduce course correction. And again, this is very tightly linked to multigrid method, reduced order modeling. You can call it whatever you want. But algebraically speaking, you can think about defining on each of your subdomain a set of vectors. Okay, so this will be used for defining your restriction operator. Using this set of local vector, you can then define a global matrix Z, which will be your prolongation operator. And then, just as for multigrid, you can define using a Galerkin product, so the triple matrix product, you can define a course operator, which this time is built algebraically from your vectors capital lambda. Of course, here I'm not telling you how to build the capital lambda, but just algebraically speaking, this is what it boils down to. And so once you have your course operator, again, just as for multigrid, you can write a two-level preconditioner, for example, using a combination of your fine-level smoother or your fine-level preconditioner with your course operator, and that's about it. So as I mentioned earlier, the million-dollar question, and it's also the million-dollar question for multigrid, for model reduction, is what to put as the lambda here. And so when it comes to domain decomposition method, we want to be able to have a very aggressive coarsening. So ideally, so in multigrid methods, the coarsening in between levels is somehow moderate. So you can expect dividing the number of unknowns in between grid by a factor of 2 up to 10. With domain decomposition method, we want to have very much higher coarsening. So we want to decrease the number of unknowns from A to AC by a very much larger factor, like 100, 1000. And so, of course, you want to be able to capture the difficulties of your operator. So to make the method converge, because in the end, if you have a very cheap method, but if it's not converging, there is no point. and ideally you want to be able to do this at a moderate cost. So this is the kind of results we can end up with. So this time this is coming from a matrix from the Soot-Sparse matrix collection. So it's not coming from a PDE. I think this one is like a circuit modeling, and so we are doing what we call adaptive preconditioning. So again, we have some sort of threshold parameter, like we saw for GAMG or Boomer AMG. We have a parameter tau, and so basically, the greater the parameter, the more numerically robust the method becomes. Of course, it has a cost. It's always a matter of trade-off. If you have something which is very robust, it's also often very costly, just like Dirac method versus Jacobi. And so here you can see that as you increase the threshold, you basically have a coarse operator which gets bigger and bigger, so it's more costly to assemble and to deal with, but you basically end up with something which converges in fewer iterates. And so you can see that with a very standard method like one level domain decomposition method, nothing converges, and so as you increase tau, you have a method that converges faster and faster. So this can be applied. Some of these techniques can be applied algebraically, like Boomer AMG and GAMG. And so in practice, it's possible to solve problems quite easily with those techniques. So there is no real point to use domain decomposition methods there, because in general they are costlier than algebraic multigrid. But there are also problems where algebraic multigrid does not work, where domain decomposition method work. And so in those instances, of course, it's nice to be able to choose a technique that converges with respect to something that breaks down. So all the results I've presented with respect to domain decomposition method are available in PETSc through a package which is called HPDDM. So it was interfaced in 2021 inside PETSc. So to have access to those methods, you need to in fact use the flag download HPDDM and also download SLEPC. Because now that you have a rather overview of the complete picture, to get those capital lambda, we actually need to solve local generalized eigenvalue problem. And so that's why we need both download SLEPC and download HPDDM. SLEPC for the local generalized eigenvalue problem. So just as for multigrid, there is no silver bullet, in the sense that we have techniques that are very efficient for symmetric positive definite systems. In some scenario, multigrid does not work, and so for this you can use HPDDM because we have a very sharp estimate of the condition number of the precondition operator. We are able to handle least square problems, so we have preconditioner for LSQR, for example. And we handle also there are various ways of building the coarse grid and whatnot. Okay, I will just wrap up with this presentation, with this slide. It will be very short, but it must be included. When you think about domain decomposition method, I've mostly focused on overlapping Schwarz method. There is also a completely different class of method which are called substructuring methods. And so in PETSc, you can use those mostly with a mat type which is called IS. So it's not a typo. There is the type IS, and there is also the mat type IS. And so this is used for splitting basically interior degrees of freedom and degrees of freedom on the skeleton of your domain decomposition. And those methods can also be made adaptive through inside the package which is called BDDC, which was implemented by Stefano Zampini. So few years before HPDDM, but he's also been working on the integrated HPDDM in PETSc. So the last part was about block decomposition. The slides are available online, so feel free to browse them, and if you have any questions, I'll be happy to help you out. Yeah, it's basically for solving systems that can be defined as block matrices, where you have blocks which can be of different type, For example, one block can be an assembled operator, another block can be an unassembled operator, a block can be a constraint matrix, which can be dense, for example. You can have 0 blocks. And so with PETSc, we have various ways to define efficient preconditioner for these using the field split infrastructure. So for example, we can define block decomposition using an additive decomposition, a multiplicative decomposition, and we can also deal with Schur complement factorization. So I'm going a little bit fast, but again, everything is online. And there is also an example in the tutorial, which is the example 7, where I'm trying this out for a Poisson problem with a single constraint to ensure the mean value of the solution to be 0. Okay, and so again, everything is online. Feel free to ask questions afterwards. And for now, thank you.
Thank you.